All right, hello group. This is General Chemistry 2. This is our online edition for February 5, 2021. So I hope that you're all aware of the quiz today. It's a short quiz. I think I gave you 6 minutes. You should be able to manage this fairly quickly, I think. Actually, so let's just jump into some of these things if I can. I'll assume the recording is going okay, and let me see if I can actually get back to my, there we go. Here's, there we go, the announcements. It takes me a while with technology, but we'll get there soon enough. So Alex, don't forget that Alex chapter 13a is due tonight. This is the first part of the chapter on solutions, and the rest of it is due on Tuesday. So by Monday, we're done with chapter 13. We'll have spent a little, basically 3 days on it, and that's enough. Don't forget lab next week. Make sure that when you come on Tuesday or Thursday that you have your materials for lab, the manual, the lab notebook, goggles. Make sure that you bring those with you. And we'll be doing the first lab. So make sure that you read through determination of molecular weight by freezing point depression. All right, now, as we move into the semester, there's one thing you need to know about me, and that is that I am not a terribly reverent person. In fact, the sarcasm, it runs pretty deep. And some of you already know that I show despair slides in class, and I readily admit it's from despair.com, so that's my disclaimer. I don't have copyright on any of these, they do. But I think they're funny, and so I'll just go through a few despair slides because we all need a little demotivation in our day. Sometimes, yes, a little affirmation is good, but we don't often get that. So let's talk a little bit about despair. Instilling the self-confidence kids will need to carry them through all the failure they experience because they weren't taught competence instead. Wow, that's a long one. One of my favorites, not all pain is gain. The journey of 1,000 miles sometimes ends very, very badly. If we don't take care of the customer, maybe they'll stop bugging us. There are a few business applied ones, so that happens to be one. The best leaders inspired by example. When that's not an option, brute intimidation works pretty well too. I hear the call to do nothing and I'm doing my best to answer it. All right, so that's enough demotivation. Notice those were all A words. Just starting alphabetically, we'll go through a few of those. It's time to pick up with solutions. So now that we're done with all of the frivolous introductions, let's move on into chapter 13. All right, solubility, factors affecting solubility. Now, as we talk about solubility in how things dissolve, primarily in water or in any solution, there are really 3 things that make a difference. The first is structural effects. A structural effect really has to do with the polarity of molecules. In the case of ions dissolving in water, we've already talked on Monday and Wednesday about the process of how salt dissolves in water, sodium chloride. Like dissolves like. Polar substances will dissolve in polar solvents. Sugar, with lots of OH groups, lots of hydrogen bonding. Sugar loves water, so it dissolves very readily. However, something like oil does not. Oil will dissolve in a nonpolar solvent like gasoline, like hydrocarbons. So structural effects make a difference in terms of solubility. Like dissolves like. Pressure effects. This is where we have a gas and water. So let's say we've got, one of the best examples of this is soda pop. In a bottling plant, they have the containers already. They're running through the assembly line. There are machines that come and they inject the solution and they inject 5 atmospheres of carbon dioxide. By putting 5 times the atmospheric pressure of carbon dioxide above the solution, that pressure is driving gas into the water. It is forcing it to dissolve. We'll give a little example of that in a minute. But that's an example of how a pressure affects solubility. You'll notice that whenever you open a can of soda pop or a bottle of something that's carbonated, when you open that up, gas is released, that gas in the headspace above the liquid. And what happens? The solution starts bubbling. Some of the gas that has been dissolved in the liquid, in the water, begins to come out because there's no pressure above forcing that gas to stay in it. Finally, temperature effects. Talk a little bit more about those in a minute. Okay, so let's say we have a gaseous solute. This is our soda pop example. As we have a gas, as we have gas atoms in this case, in what I'm calling the headspace, the vapor stage above the liquid, there is an equilibrium that occurs. So there are molecules or atoms of the liquid that evaporate and gas phase molecules that are in equilibrium that will then condense. So we have this equilibrium that will go back and forth. As we put pressure on this, as we compress the gas above, we skew the equilibrium so that more of these atoms are going to be in the liquid state. And then finally, under the new pressure, we reestablish equilibrium again. The equilibrium is a key concept. We're going to spend about 3 chapters talking about equilibrium. And this is a really good example of a simple equilibrium. Equilibrium between the gas and liquid states. We have evaporation, the green arrows. We have condensation, the red arrows. And so what happens is at equilibrium, that doesn't mean that the atoms here are equal to the number of atoms here. What it means is for every atom that evaporates, we have an atom that condenses. So the rate at which evaporation and condensation occur, the rates at which they occur are equal. All right. Now, I'm going to throw this out there, and I'm not planning that you work any problems with this. But this is Henry's law, and you should just know what it is. How much gas is dissolved in a liquid depends upon the pressure of the gas above it. And so it's a very simple equation. Concentration is equal to a constant times pressure. It's very simple. So you can work through this on your own. What is the carbon dioxide concentration? What is the molarity? By the way, square brackets always mean molarity. Square brackets always mean molarity. What is the molarity of carbon dioxide in soda pop with a partial pressure of CO2 at 5 atmospheres? Here is the constant. These constants are available in textbooks. You can look them up. You can find them on the internet. They're not all the same on the internet, so we're going to use the constants as the book gives them. So here the constant is 0.031. This is not a very big solubility constant. So then you can find the concentration. All right. I'm going to try to move quickly through some concepts of solutions. And one of the most challenging is vapor pressure. Now, we talk about vapor pressure in Gen Chem 1. You have heard it in your courses. I don't know that any of you had Gen Chem 1 from me, which is probably a good thing. But what happens here with vapor pressure is as molecules evaporate in a closed system, let's say we're to close this lid right here. As molecules evaporate, more and more will evaporate until you reach a point where some of these molecules in the vapor phase begin to condense. At the point where we have equilibrium, the pressure of the liquid now in the vapor phase is the vapor pressure of the solution. So let me try to say that again. Probably in the same words, maybe not. So if we close this container, the liquid will evaporate until we build up enough molecules in the vapor phase that they start to condense. So as more and more evaporation occurs, we begin to build up more molecules here in the vapor, and then they start to go back into the liquid until we now have equal rates of evaporation and condensation. We reach equilibrium with regard to that. At equilibrium, in our closed system here, the partial pressure, or the pressure of the liquid that has evaporated, is equal to the partial pressure of the solution. So the pressure of the vapor pressure of a liquid is at a given temperature is equal to the pressure of that gas in the vapor phase. Now, what if we have a solution? Let's say we have a solution like this. We have a solution here and pure water here. Both of these have evaporation that occurs. Both of these will lose solvent. Well, what happens? In the case of a solution, we now have a solute in here. Notice these little blue particles, they represent solute. Obviously, these are not actual size. So what happens is when we have solute, think of the surface of the liquid. If we have the surface of the liquid, that is where the molecules are evaporating from. But what if we have solute particles here? The solute particles cannot evaporate. That's the assumption we're making. So if the solute particles can't evaporate, they are taking real estate, surface area, where liquid molecules would normally be. So we have, of our surface, less molecules are free to evaporate because we have solute particles there. The vapor pressure of a solution is always lower than the vapor pressure of the pure solvent. Get that? The vapor pressure of a solution. We have fewer molecules of the liquid that can evaporate in a solution because of the solute particles compared to that of the pure solvent. Because the pure solvent doesn't have any solute particles there to help that block that evaporation process. That doesn't mean we don't get any evaporation from a solution. It means that it occurs to a lesser degree. So what happens then is if we get water vapor from both of these in the same closed space, we get water vapor here. As water vapor condenses here, it's less likely to leave. So over a longer period of time, we get this. All of the solvent will eventually go over here into the solution. This starts out more concentrated, and it ends up more dilute. All of this by way of introduction to colligative properties. Colligative properties, this is really the main theme of chapter 13. It's the second really key idea in chapter 13. And here's what colligative properties are. It's a numbers game. It's how many particles you have in solution. That's why moles are very often part of these calculations. Colligative properties depend only on the number of solute particles in a solution. Doesn't matter what they are. It only matters the number of them you have. And these are the four areas where colligative properties manifest themselves. One is vapor pressure lowering, and we've already talked about this. By the fact that we have solute particles in the solution, we have a lower vapor pressure because we don't have as many solvent particles at the surface of the liquid. We have the lowering of the vapor pressure. That is a colligative property. It doesn't matter what that solute particle is, it only matters how many of them we have. The second colligative property is boiling point elevation. The third one is freezing point depression. And these two are related. These two are related. Having a solute in a liquid raises the boiling point and it lowers the freezing point. We'll explain why in just a moment. The last colligative property is osmotic pressure or osmosis. This is really a unique one. This is really a powerful one. And we'll have calculations related to each of these four colligative properties, and we'll talk about them in order. Vapor pressure lowering. Remember Chi? Remember Chi? Of course you do. This is what we just talked about on Wednesday. Chi is mole fraction. And if 1 represents the liquid phase, let's think of this as a liquid solvent, let's call it water, and a solute that doesn't evaporate. If we're using 1 as our solvent, this is the mole fraction of our solvent. This would be moles of water over total moles. That's Chi 1. This is the original vapor pressure of the solution. This little naught sign, that means the vapor pressure of the pure solvent. So water at a given temperature has a specific vapor pressure. These are known, these are well published. So this is a fixed value at a given temperature, Chi. That is the mole fraction. It's a concentration. It's the mole fraction of the solvent. And so if this is 0.9, then this is going to be 90% of this number. If Chi is 0.9, let's say if 9 out of 10 molecules present are solvent, then the vapor pressure is going to be, the actual vapor pressure of our solution will be 90% of that of our pure solvent. Okay, this is a little bit different because we're used to calculating mole fraction of solute over solvent, of solvent over total moles. Solute divided by total, as opposed to solvent divided by total. If we change Chi 1 to Chi 2, now Chi 2 is the solute. Remember, 1, solvent, 2, solute. The change, we can rearrange this so that the change in vapor pressure is equal to Chi 2, the mole fraction of our solute, times the original vapor pressure of the liquid at a given temperature. And that's what these are all explaining. Okay, so let's move on to the next one. I don't want to spend any more time at the moment on vapor pressure. After all, I've got a whole lot of material to cover in like 5 minutes, so if I can't cover it all, I'm just going to start talking faster. All right, actually, we've got a little more time than that, but I just make stuff up as I go along. By the way, you should know that only about 70% of what I say in class is true, and it's your job to figure out what that 70% is. So now that we're clear about that, let's take a look at this. Boiling point elevation, freezing point depression. This is a phase diagram. You know what phase diagrams are. We talked about these in Gen Chem 1. Let's revisit it. This section over here is the solid phase. This is the liquid phase. This is the vapor phase. The axes, pressure, temperature. Pressure on Y, temperature on X. The red is for water. This would be the normal phase diagram for pure water. What happens as we add a solute to it? Let's say we put some salt in it or some sugar and we dissolve it up. Let's call it sugar. We make some sugar water, we dissolve it up. What happens to the sugar? Well, we know that the vapor pressure gets lowered. We know the vapor pressure gets lowered as we add more solute because we've just talked about why. What happens and why? If the vapor pressure is lowered, think about what our definition of boiling point is. Boiling point. The boiling point of a liquid is the temperature. Actually, it's the pressure. It's the temperature at which atmospheric pressure is equal to the vapor pressure of the liquid. So you put a pan of water on the stove, turn it on, heat it, and it starts boiling. Why does it start boiling? It boils because the vapor pressure of that hot water is equal to atmospheric pressure. The two pressures become the same, and that's when boiling happens. Liquid converts into vapor. If we add a solute to that, like sugar, something that doesn't evaporate, we have to put more energy in so that that low solution that now has a lower vapor pressure, it's got more energy. We've got to put more energy into it so that the solution does have the same vapor pressure as atmospheric pressure. We have to put more energy in to raise that vapor pressure. That's why vapor pressure shifts higher. This delta T, it's a change in the boiling point. This is the difference in the change of the boiling point between normal water and a solution that contains water. On the other side, freezing point depression. Notice what happens. This is the freezing point of our pure liquid, pure water. As we add a solute, like sugar, that lowers the freezing point. This is a little bit more complicated theoretically, and I'll talk about this more in a couple of different ways. Maybe not all right now. So think about having a solution. I can do it over here. So let's say that we've got our solution. Turn this way a little bit. This, excuse me. The blue is a solute particle. And let's say these little green dots are solvent. Let's call it water. Let's say this is water surrounding a sugar molecule. If we're going to put this in a freezer, we're going to form ice. We're going to convert liquid water into ice. We're pulling at heat and thermal energy out of it. What happens? Well, we've got water that's not connected to this, that starts to coagulate, coalesce, come together, freeze. And we're going to start forming a solid. But some of the particles, some of the solvent is involved in hydrating the solute. It takes energy to pull the water away from that, because when we form ice, ice is simply pure H2O. The ice does not have any impurities in it as it forms. Let's think of it this way. As we have, I'm not doing this well at all. Okay, let's say that all of these little green marks are water. As they start to freeze, they form a crystalline lattice. Water forms that solid crystalline lattice. As that solid lattice of ice forms, it excludes any impurities. So let's say we start to freeze it here. Let's say we put a ring around this and make this really cold. This begins to form ice. As this ice forms, any solute impurities, they get pushed down the road. They don't want anything, this ice doesn't want to include them. That takes way too much energy, forming these perfect ice crystals. So what happens is, as we slowly freeze left to right across this pond of water, as we freeze and hit near the end, what happens is all of those solute particles end up down here. If you ever think of it this way, you stick an ice tray in a freezer, fill up an ice tray with water, you put it in the freezer. When it's frozen, you pull the ice out. Is that ice perfectly transparent? Usually not. And the reason that it usually isn't is, how does ice in an ice cube tray freeze? You put it in the freezer. All of that thermal energy from the water that's in, let's say, in one cube of the tray, one of those depressions in the tray, it's losing heat from all directions, but from the outside of the solution. So you start to form the shell of ice outside. And as more and more heat leaves the ice, leaves the water, it freezes from the outside in. So that all of the impurities that were in that water, no matter how trace, get pushed to the very center. So this is why, if you ever go to, let's say, a gas station or convenience store and you buy a bag of ice, sometimes it comes as cylinders and you'll see that the center is knocked out. The reason they will knock out the center is because the ice freezes from the outside in, all of any impurities are in the center. They punch out that center, you've gotten rid of all the impurities, now you've got pure H2O in ice form. It's very clean, there's nothing else in it, you're not going to have any flavor from minerals that might be dissolved and so forth. Okay. The bottom line is, for solutions, the boiling point of that solvent gets raised, the freezing point gets lowered. Another practical application of this is why they put salt on the roads in the wintertime. They put salt on the roads because, think of it, you've got ice. Let's say you've got ice or snow. You put salt on there, and what happens? That salt hits the ice. You get interaction between H2O and NaCl. And you form a solution. It's usually a very concentrated solution of sodium chloride. That even at temperatures below 0 Celsius, below 0 Celsius, below 32 Fahrenheit, even at lower temperatures, that salt now becomes a saturated solution, and that saturated solution has a boiling point much lower than that of pure water. So that's how salt melts ice. That's why they put anything like calcium chloride or calcium acetate. Sodium chloride is very commonly used. That's why they do that, because of this particular phenomenon. So for boiling point elevation, here's what we have. We have a non-volatile solute. What does that mean? It means that whatever our solute is doesn't evaporate. It could be salt. Salt doesn't evaporate. Salt stays behind. It could be sugar. Sugar's not evaporating. So a non-volatile solute. And again, we're just talking about water here for pretty much all of our calculations. We have fewer particles of the solution at the surface. So actually, it's fewer particles of solvent at the solution. We have less solvent molecules at the surface. We have a lower vapor pressure, which means we have a higher boiling point. This is the equation. It's a simple equation. Okay, T sub B is the temperature of boiling. In other words, boiling point. Delta is the change. How high is that boiling point raised? Let's go back to the previous slide. How far does this get pushed up? What is delta T sub B? What is the shift in boiling point? That shift in boiling point is equal to a constant, which you have to be given, times little m. What is little m? You know what little m is. It's molality, moles of solute per kilograms of solvent. Molality. We've been working with that for the concentration conversions. Times I. It's a simple equation. The change in boiling point, how much higher is it raised, is equal to a constant times molality times I. So what is I? I'm glad you asked. I is called the Van't Hoff factor. And it's really not that difficult to understand what this is. The Van't Hoff factor, this little I, is equal to the number of particles that dissolve per formula unit. For example, if we have sugar, sugar is sucrose. It's a single molecule, bunch of OHs on it. Sugar, when it dissolves, you get one particle per formula unit because one sugar molecule dissolves into one molecule. But for sodium chloride, when sodium chloride dissolves, our unit is NaCl. For NaCl, when that separates, we get one sodium ion and one chloride ion. In other words, excuse me, I'm getting emotional about chemistry again. So when NaCl dissolves, you get two particles, one Na plus, one Cl minus. Excuse me. When we have something like MgCl2, is magnesium chloride soluble or insoluble? Magnesium chloride, quick, soluble or insoluble? Excellent. It is soluble because chlorides are generally soluble. Magnesium is not one of the exceptions. When this dissolves, magnesium chloride aqueous gives us a magnesium 2 plus and 2 Cl minuses. Notice what this is not. This will make me very, very unhappy if I see this. It is not Cl2. It is not molecular chlorine. It is 2 chloride ions. That's why we would call this magnesium chloride. There are 2 of these for every magnesium. Not this. It is not Cl2. Magnesium and 2 chlorides. That's a total of 3 particles. 1, 2, 3. 1 formula unit, 3 particles. So I, little I, the Van 't Hoff factor, would be 3 for magnesium chloride. All right, so this is somewhere in table or chapter 3. I think it's page 592, but I'm not going to guarantee that. These are constants for Kb, and these are the constants for Kf. So for water, the first one boils at 100 degrees C. This is Kb for water. Notice that the values for Kb and for Kf are different. They're not the same. Boiling and freezing, those are 2 different constants. There's different mechanisms that are going on here. Benzene, ethanol, acetic acid, and cyclohexane, those are just other liquids. All right, freezing point depression. Just like boiling point is elevated, freezing points are depressed. How far? Same type of equation. Delta T sub F, this is a negative now. So for water, which is at 0, delta T sub F is going to be how far below 0 do we go? For boiling point elevation, our boiling point is 100. So if delta T is 3 degrees, our boiling point is not 3 degrees. Our boiling point is 103. It's 100 plus the 3, the change of delta T. So this is freezing point depression. It's the same type of process. Okay. So let's work through this problem together. So we've got 20 grams. Let's see. Write it down. A solution has 20 grams of a non-electrolyte. Write it down here. And this is solute. In 500 grams of benzene, which I'm going to abbreviate BZ because I don't want to write it all out. The freezing point of the solution is 3.77 degrees C. 3.77. The freezing point of pure benzene is 5.44. So I'm just writing down all the data. And by the way, this is a good way to approach problems. When you have something like this, take all the key data and just write it down and label it. I'm not doing a great job labeling here, but nevertheless. Kf for benzene is 5.12 degrees C. Degrees C per molal. What is the molar mass of the unknown compound? Okay. Now we can do the problem. The kind of problem, freezing point depression. Delta T sub F is equal to minus Kf molality I. We're talking about a non-electrolyte. A non-electrolyte, I equals 1. I is 1. The molality, we don't know the molality. Do we know delta T sub F? This is the boiling point of pure benzene? No. This is the boiling point of pure benzene. This is the boiling point of the solution. The difference between these is 14 minus 7 is 7. 3 minus 7 is 6. 1.67, and that is degrees C. These are degrees C. You're going to want to check me on this because I'm kind of making it up. Remember that 70% rule? So this is what I'm calling delta T sub F. This is the difference in boiling point. Actually, the boiling point depression is minus. This is equal to minus K sub F. K sub F is this, 5.12 degrees C per mole L times molality times 1. So I'm just going to leave it like this. Now we have a very simple way to calculate molality. We divide both sides by, by the way, it has a negative sign up front. We divide both sides by 5.12. Let me see what I have. So the molality of our solution, let's see. Calculator, 1.67 divided by 5.12, 0.326. And that is equal to moles, solute, all over kilograms of benzene. How are you doing so far? Follow what I've just done with this problem? Excellent. All right, this is the change in temperature between, it is the lowering of the boiling point, minus 1.67. This is minus the K value times molality times 1. Okay, now that I know the molality, I can calculate moles because I know how many grams of benzene I have. I know how many kilograms of benzene. This gives me a number of 1.63, 0.163 moles. Sorry. I think. Yep, 0.163. Now, what do we ask for? What is the molar mass of the unknown compound? I know grams, I know moles. Mass over moles gives us molar mass. So go ahead and do that calculation. 20 divided by 0.163. $122.6, or 123 grams per mole. Beautiful. It's a beautiful thing. Okay. I think we're going to stop here for today. And I'm going to post this video. I'm going to post this video and finish up the rest on Monday. All right. Hey, I hope you all have a good weekend and make sure that you finish up Alex for tonight.